Okay, so at the end of the last video, I had said to you that if I were to assign you anything to do from that video to this one, it would be to look up and find at least the name of the 4 quantum numbers. If we were in school, it would have been your homework. You still have your atomic assignment to work on and other things, so I knew I didn't need to give you too much, and really there's no calculations here yet. Today we're going to look at the 4 quantum numbers. Okay, the first one we've actually already met. It's called the principal quantum number. The principal quantum number. And we met it when we were looking at Bohr's model of the atom. Its letter is a small n. And this is presented to us by Niels Bohr. And that was 1913. I don't think if it was 11. Rutherford was 11 and Bohr was 13. And the principal quantum number tells us the energy level, or the shell, that the electron is in. So it tells us energy level. Okay, so n equals 1, n equals 2, etc. The bigger the value of n, the further away the electron is from the orbital, the bigger the shell. It can have values from 1 all the way up to infinity. Okay? So that's the principal quantum number. That's number 1. The second quantum number, number 2, is usually called the, be good if I could spell orbital, the orbital angular momentum. The orbital angular momentum quantum number. You will also sometimes hear it referred to as the azimuth, and I don't ever use it. azimuth, azimuthal, I guess, quantum number. Shorter, but harder to spell, although I did spell orbital wrong. The letter for this quantum number is a small l. This quantum number is brought to us by Arnold Sommerfeld, and some of you had him as your person to do research with, for. And the year we believe is probably 1914 to 1915. Okay, what is this quantum number? This quantum number is related to the angular momentum of the electron. Related to angular momentum, which really probably doesn't say too much to you. You know what momentum is. An angular momentum simply means it's moving in a circle. But maybe it would be easier if I said to you it tells us the shape of the orbital. Okay, it tells us the shape of the orbital that the electron is in. Okay, so it's describing, really it's describing the subshell. Describes the subshell. Okay, the shape of the orbital. That's number 2. And I said it was L, yeah? Okay. Number 3, the magnetic quantum number. Oh, I forgot one thing above. I knew there was one more thing I was supposed to do. Come back to that one in a second. The orbital quantum number can have any values. L can be any value from 0 all the way up to n minus 1. So if n is 1, L can just be 0. If n is 3, L can be 0, 1, and 2. If n is 8, L can be 0, 1, 2, 3, 4, 5, 6, and 7. Okay, so L will have values all the way up to n minus 1. All right, magnetic quantum number, its letter is M with a subscript L, okay? And it is related to the direction of the angular momentum. Direction of angular momentum. Okay? In other words, it tells us about the orientation of the orbitals. Orientation, or the direction of the orbitals. So the orientation of the orbitals. This number is also brought to us by Arnold Sommerfeld, about the same time period. Okay, I suspect it probably came, he probably published it at the same time or shortly after. So we say 1914 to 1915 in here as well. Okay, its values, oh, I'm getting that light again. Its values are from L, all the, negative L through 0, all the way up to L. Okay, so if L is 0, then ML is going to be just 0. If L is 1, then ML will be -1, 0, and +1, right? So if we do an example, let's say L is 2, then ML will be -2, -1, 0, 1, and 2. Okay? And so its values go from -L all the way up to L. All right? And then the fourth one is called the electron spin, or sometimes just spin. Electron spin, put electron in brackets, spin quantum number. The reason it's not always referred to as electron, because protons and neutrons can also have quantum numbers. So the spin quantum number, and it is ms. Okay? And it tells us about the direction of the spin on the electrons are spinning on their axis. So it's telling us if there's spin, so direction of spin. So imagine them like little tops or whatever, spinning clockwise or counterclockwise. And we usually show that as a spin up or a spin down. Okay? It can have two values. It'll either be 1/2, just broke my pen, I think. It will be 1/2, or it will be -1/2. Okay, those are the two possible values. This guy is brought to us by Pauli, Wolfgang Pauli. No. Is that his first name? Anyway, it is brought to us by Pauli. Now I'm worried I didn't get Warren Heisenberg. Yeah, it is Wolfgang Pauli. I just worried I had his first name wrong there for a minute. And this was around 1925. So significantly later. So like 10 years they were trying to figure this out, from when Sommerfeld figured out the second and third till Pauli got the fourth one. About 10 years in between there, okay? Now, so what the heck are these quantum numbers? Like, how do they make sense? Think of them maybe as an electron's address. We're trying to find where an electron is in an atom, and the 4 quantum numbers can tell us that. Okay? And so it's like the electron's address, where the principal quantum number is like the country, and the orbital angular momentum is like the province, and then the magnetic quantum number is like the city or town, and then the spin quantum number is like the street number, right? The street and the number, okay? And one of the things that Pauli figured out, which led to his to this quantum number, was that no two electrons within an atom could have the same 4 quantum numbers. Just like no building in a city or a town or in the country could have the same address. Like they might be in the same country, they might be in the same province, they might be in the same city or town, but their street number at least will be different. Okay? And so if you think of the 4 quantum numbers like that, it will help. The only reason that's not a wonderful analogy is simply because a street address will give you a pinpoint place if you put it into Google. For electrons, it's the probability of finding them in that spot. So we still can't totally pinpoint them, but we can get this will give us the area that they are, the area in the cloud where they are, okay? So these are the 4 quantum numbers. When we come back, we'll talk about Pauli exclusion principle.